Thanks for introducing me. My name is Nitin Suresh. I'm right now in California. I'm going to talk about optimal handling video compression for datasets for computer vision. We don't have to go over this. You just introduced. Thank you so much. I've been at Google in various teams, including augmented reality and virtual reality. And my background has been in camera image quality and video quality in general. Me and Dr. Yu also spent a brief time in Georgia Institute of Technology. That's how I know Dr. Yu as well. Overall, I don't have many slides over here, but these are the topics which we will discuss. Why exactly we need data sets for computer vision, and what are the various purposes of it, the various types in which you can store it, whether it is uncompressed, compressed, etc. That's one part. Then we will discuss how we handle this for various computer vision algorithms. In particular, we will talk about things like motion tracking and plane detection, and also provide resources to many other AR core computer vision algorithms so that researchers like us can, can experiment with many of these. And then I will leave the floor to open discussion to make sure we can answer all the questions as needed. Overall, what is the purpose for dataset recording and playback? There are several reasons to do that. One is, of course, machine learning algorithm development. So you as an engineer could be developing several computer vision algorithms, things like motion tracking or plane detection, post detection, etc. For that, you need to have a good quality and good variety of data sets. So that is one part. Then once you have this computer vision algorithm, how do you know whether it's good or not? You need to do a lot of testing, you need to do debugging, both the algorithm as such and how it interacts with other computer vision algorithms. Those are the key performance indicators, KPIs, and accuracy overall. Also, given a computer vision algorithm, you can scale it according to the situation. So that's where the power performance attributes come in. And once you have a computer vision algorithm, you don't know whether the same, like different scenes work for that algorithm or not. So you'll have scene debugging, etc. And of course, once you have all these algorithms, you need to prototype specific ones. You could be walking in an airport. You want to have a ride sharing algorithm. So for these dataset recording and playback happens. And it should be usable on many platforms as such. So it should be easy to store, easy to view. Throughout my presentation, I will point to some resources along the way related to items that Google has released in the past for AR code. At the bottom, you have one such thing, the recording and playback for AR core. What we do is AR core is a backend for the algorithms on the Android ecosystem where you can have on augmented reality applications. Once you have those apps, how do you know whether they work fine or not for a given scene? There we help folks do dataset recording and playback where we record it once, and when you play back, the phone behaves as though things are happening live. For example, you have a plane detection app or a desk detection app. You can't keep capturing the exact same scene each time. So you capture it once, and when you play it back, the same thing happens. The phone behaves like the recording is happening. I mean, the live cameras are happening, and that's how this is useful for debugging. So this is what we have released right now. Let's talk about the various requirements for various dataset recording needs. For machine learning algorithm development, what do we need to do? There should always be ease of capture. It should be easy to capture because you want to have various scenarios, situations. So that should be there. And it should be easy to store and easy to store in a privacy agnostic way. So making sure that when several folks are there, it should be able to be anonymized and it should be able to be retrieved, etc. At the same time, it should not take so much space. But for machine learning algorithm development, you want to capture as high a quality as possible. And of course, you want a large volume of data sets, large quantity. You want a large diversity of data sets. You don't want everything to be captured by just two, three engineers in their office space or something. That wouldn't scale to what the customers actually use for. So that's one requirement for the ML algorithm as such. And then you need to be able to be annotating it easily. For example, if you have plain detection or scene semantics, it should be easy for a bunch of engineers to be able to mark what is this, what is, say, a tree, what is a road, etc. So those things are there. And we should always have a good high frame size, frame rate, image quality. Whenever we develop machine learning algorithms, we actually don't know for sure sometimes what resolution you want to use. For example, are you going to use HD video? Are you going to use 6 VGA? Are you going to use 60 frames per second? As an engineer developing it, you don't want to spend too much time worrying about what resolution you'll be using it. In the end, you may actually choose to do QSIF, etc., just because it's what the power and performance threshold on the device permits. But you don't want to worry about that during the machine learning algorithm development. So you want as high a frame size, as high a frame rate, and as good image quality as possible. When you train your algorithm, you may be training on a compressed version or a point cloud version, etc. So the quality may not matter in the end, but when you're developing the algorithm, you don't want to be constrained by those. You can always compress, you can always degrade the quality if needed. So these are the dataset needs for machine learning algorithm development. What is it for testing and debugging? The ease of capture always is the same. It should be easy to capture. In fact, it should be even easier to capture than the machine learning algorithm development. When you have, say, a phone app, you want it to be captured on a phone. For machine learning algorithm development, you can capture in a high-res Samsung camera, for example. You can capture that and then downscale it, degrade it. You can do all that. But when you capture it, you should be able to capture the data sets while you are doing the app, while the people, the customers are on the field, etc. Similarly, the ease of storage is even more important for testing. Why is that? For a machine learning algorithm development, you can store uncompressed raw, you can store gigabytes of data sets and you can just put it on the cloud, etc. You can do that. But when you have mobile devices, when you have a phone with limited bandwidth, limited storage, and limited upload capacity, you want people to be able to capture it very quickly, store it, and possibly upload it for folks to use. So that is useful. And of course, the volume, quantity, diversity are all important as well. And you should also be able to annotate easily. In fact, annotation is sometimes more important and different for the testing needs. A viewer on a phone should be able to see the video. It should not probably be blobs of uncompressed things which cannot be shown on the screen. The user should be able to see the video and select segments of the video or image capture to upload as necessary. And the frame size, frame rates, all those are important, but you have to strike the right balance. Is it necessary to be pristine image quality? Maybe not. It is more probably important to have smooth frame rate than high resolution image quality, which you can zoom in and see. So this is why it comes to the talk over here, why sometimes you need to compress the data sets. Quality should be as close to the live use case as possible because you're trying to debug. When you have a test app where you're trying to place an object on the table and it doesn't work in a specific customer's house or something like that. You want to be able to quickly capture that data set and be able to the user should be able to annotate and send it to us so that we can debug it, those things. And of course, we all know Heisenberg's uncertainty principle, where you don't like the measurement shouldn't actually interfere with the state. So if a certain thing is working in a certain way, the app, computer vision algorithm, the very point of trying to capture the data, right, shouldn't interfere with the results. That is very important for dataset recording, for testing and debugging. And of course, as we said, ease of analysis and viewing. Now let's talk about the uncompressed versus compressed advantages and disadvantages. What are the advantages of compress? Sometimes it's not possible to capture at full quality. If you ask the ML algorithm development engineer, they would always want 4K HD at 90 FPS for like some 30 minutes. But that's not possible. We just cannot capture it at full quality. You don't have the storage, you don't have the bandwidth, and you don't have the power and performance for it. You will have frame drops. You just simply don't have this hard disk space to do that. And sometimes it is not necessary to do uncompressed at all. You could see side by side the compressed and the uncompressed, and you just cannot see the difference visually or through computer vision. And many times, if you look at the machine learning algorithm development, the algorithm itself would have been trained on a compressed version, such as JPEG. And the algorithm could also be downsampling frame size, frame rate. And in many cases, humans can spot differences, but computers, as you all know, are very smart. Computer vision is resilient. We have engineers like you who have been working for decades, for a long time on these algorithms, and many of these algorithms are very robust that even if you have visible compression artifacts, they are fine. Of course, it should not be too compressed because who knows if some future algorithm could be not performing to it. But you don't need to have an uncompressed. And as you know, the cameras and the sometimes on devices, you have the cameras themselves streaming as a compressed version to the image signal processor and decompressing things like that. So it doesn't make sense to engineer around those bottlenecks. And of course, it's easy to handle. When you have a compressed data set, you can very quickly upload to and from device, and you can view it in standard video players. As an example, when Google Street View had an app for enabling users to go around in places where there was no street view and upload the scene to Google Maps, we used the ARCore MP4 compressed format because it's easier for users to quickly capture and upload. So that it populates in Google Maps in a way that mimics the scene exactly. All this is for compressed data sets. What about uncompressed data sets? Sometimes it's actually useful and advantageous to use uncompressed data sets. Let me explain why. If you have a specific device like a phone and you want to know how much power, performance, CPU, thermals your algorithm takes, say you have plane detection or pose detection, how would you do it? You could use compressed data sets, but the answer wouldn't be exactly accurate because in the live use case, you have cameras and ISP being used. In the playback use case, the cameras are not used, but the codec and decoder are used. You could theoretically profile it and do a delta as a baseline and go over it, but this is many a times not desirable for the accurate power performance measurements. So for the power performance measurements, it is more preferable to have uncompressed dataset playback so that at least the video decode aspect is not interfering in your measurements. We can always switch on the camera to have the corresponding power performance for the camera. But for power performance, it's generally better to do uncompressed playback, unless you have some special hardware to do the decode just in the side without using the actual hardware, but that's very rare. And sometimes actually computer vision algorithms can be impacted by compression. Sometimes even humans cannot spot the differences, but the computer vision algorithm is sometimes sensitive. These are typically cases where it's still under development and not robustly landed. Here are some examples where the computer vision algorithm can be affected by the compression, even when humans cannot see. When you have a history of previous computes, there are some algorithms like that. Like, for example, very accurate motion tracking algorithms. For that, you need to be mindful because the videos could look just like the uncompressed. But if you want less, like a few centimeter accuracy for long data sets, then compressed will probably not work. Similarly, accumulation of errors and integration with different algorithms. When you have 5, 6 different computer vision algorithms and you want to land all of them together, many times compressed may be fine, but because of the nature of hardware processing, etc., there may be some errors and you'll always have doubts. Why is this not working fine? Is it due to the compression or due to the uncompressed? To avoid such doubts, it may be beneficial to sometimes use uncompressed. And we have some algorithms where you zoom and crop. As researchers, you may be implementing several computer vision algorithms. For example, the Google AR Core provides standard APIs for some computer vision, but you could also query a standardized image API and do your own machine learning. And you could do things with zoom and crop, etc. For that, it's better to record as high as possible because we don't exactly know how much you are doing digital zoom and crop for it. That's one. And here are some other examples where compression may be tricky. Like you have Google Lens and you want to do a frame selection where you select the sharpest frame without motion blur and send it upstream. But you want to have the flexibility to choose the sharpest frame. When you do compression and the rates are a little lesser than optimal, the IPB encoding may not match your use case. So what is the sharpest frame may not be the sharpest frame now based on how you have done the IPB encoding for it. By the way, if anybody has any question right now, I think we are asking at the end, but if you would like to interrupt in the middle also, feel free to, or just make a note and we can come back. Let's talk about some of the compressed dataset AR code format. If you use a standard Android phone today, you can use the sample apps or the API to capture datasets. They typically are video tracks or audio tracks, and you can do custom data tracks. The video tracks, you have multiple resolutions. If typically it's the lower resolution by default, you can also add the higher resolution. We right now encode using H.264. It's lossy, as we spoke about, but perceptually lossless. The bitrate, the settings, they are heuristically adapted. Audio, you can use it, but you have to use it as part of the custom data track. In the custom data track, we right now have not exposed the actual container, but they are pretty much standard protobufs where we pack things like gyroscope, accelerometer, location, IMU temperature, and several other data like that. You can actually pack your own data into the AR Core for external track. You could choose to do something specific to your algorithm, tabs, etc. Here are some links to which you can access it if you are interested. We have AR Core samples, and the samples have several things like plane detection or scene semantics. That's a fun thing. You can pointed, it segments the trees, it segments the roads, cars, it tells you, and you can use it in your app. We have geospatial anchors, we have object anchors, etc. Then this is an interesting app called the Depth Lab. You can use it and see how to explore and calculate the depth of the scene. You can see all the APIs in the code samples there. And then we have the record and playback, which you can use and which you can use to playback in your own app to prototype yours. Previous customers have done it things like you want to scan a room, so you record it, and in the post processing you can build the room location. These are some of the things which you can do for your app. Once you capture the data sets, you can view them in standard players. For those of you who are not familiar with how to view multiple stream videos, if you capture a stream, for example, with 640 by 480 and 1920 by 1080, all packaged in the same thing, you can use standard video players. An example thing is Video LAN client, VLC media player. There you just go to the video and select the video track. You select all the video tracks and both of them plays on your computer at the same time. Okay, so that's how you capture data sets and do it. Now let's talk about how some of these algorithms are tolerant to bit rates. And the experiments which you see here are what we have done at Google and use that to proceed with dataset capture for few algorithms. A brief heads up on the results. We find what are the bitrate settings, etc. for various algorithms. And we ended up going conservative for the thing. So if you use the Android AR Core sample apps, you will actually see a high bitrate, closer to 8 Mbps, which is much more than what we observe is needed. So what are the different compression methods we do? We use H.264. That's what we have publicly released. We have on Linux tools, we have on device tools. We experiment with various iframe rate, key intervals, fixed bit rates, variable bit rates, adapting the quantum Q step in the H.264 encoding for those who are familiar with it. And we have several tools that look at the data sets and come up with KPIs. Here is an example of a data set where I take the phone and walk around an object and we get the pose and the point cloud. These are sample tools which we use to do the analysis. So what did we do? Of course, we have several phones, we have several data sets. We pretty much captured a bunch of them. Before doing the compression, we wanted to see what is the uncompressed version. It's the ROSBAC format, which is the uncompressed format. And so we did a few things. We captured the ROSBAC. We also have the Vicon to have the ground truth of the phone so that we know how the actual pose happened. And we also did compression of the ROSBAC to the MP4 and then saw how the previous tools like the post detection behaves for various compression. We can discuss what all KPIs we have used, and I'm going to list some of here. One thing is the global root mean square error to the Vicon. So if you took in a medium environment, you walked around the office in a circle, and then you came to the center. For the entire circle, if you compare the ground truth Vicon and compare it to the actual predicted one, how much was the error? As you can see, when the bit rates go less than 2 Mbps, till 1 Mbps also it's okay. But when you have tricky data sets, like you close the camera and move it back, you have sudden changes in light, you have low light and shakiness, and you aggressively rotate it. For items like that, between 1 and 2 Mbps, they start to break down. And by the way, this is all for 640 by 480 VGA at 30 FPS. For this Actually, it's okay to have even one Mbps. With 1 Mbps, for most of the scene, we just had only 1 centimeter of error. So what this means is when we have several clients, both internal and external, and they want to help us debug the motion tracking algorithm, it's okay to record even at 1 or 2 Mbps and then upload it. If an engineer says, hey, I took my phone in my room, I moved it over here, and then suddenly things drifted off, or I was supposed to be back at the same spot, but the AR object I put on the table just moved by a meter. Then we upload the data set and when we debug it. So while 2 Mbps is a good answer, as I said earlier, we do it at a conservative, much higher, roughly around 8 Mbps to be doubly sure that we are not missing anything. So this is one of the experiments which we did. Other experiments which we use as KPIs are the metric position error, the global and the local percentile position error. The For each of the path, we see this is the part which I'm not very sure about, but because I have to check with the teams that did this. And we measure the error for the entire one, and for the local, there's a sliding window, and we make sure we sort it out in a bell curve and see the 95th percentile and see what is the error for it in centimeters. So even for that, it turns out that 2 Mbps is these 2 Mbps, 1 Mbps is a safe bet to see how we can compress these data sets. We want to be sure and conservative, so we did several other experiments. We did items like dropped posts. When you walk around, does a post suddenly drop? When you have compression artifacts, they get blurry. And as many of you know, the way motion tracking algorithms typically work is they take the image, they process for features, they try to match the features. There are several ways to do it. So when you have a sudden jerk in the motion, you may have a dropped pose, or you may have a reset. These are the KPIs which we have done for motion tracking. We have several other results for other computer vision as well. This is something which I just took in my room right now for plane detection. For plane detection, tolerance to bit rate, I can show examples of a high bit rate versus a low bit rate video to show what happens. So an example scene is a data set with a fast sweep or a slow sweep. When you have a high bit rate, whether you sweep the phone fast or slow, you still get the planes because the artifacts are pretty good. The point clouds, all that are captured and you get it. But when you go down to something very bad like 700 kbps, this for 60 fps by the way, only the slow sweep triggers actual plane detection and the fast sweep doesn't work because things are so blurry. So as you can see, this is an example where it shows how plane detection deteriorates with various bit rates. So to wrap things up, tolerance to different computer vision algorithms, we have several algorithms such as motion tracking, plane detection, scene semantics, things like that, depth. Some of the more sensitive ones are motion tracking, and that is the reason why we use that for benchmarking in a more conservative fashion. Why is motion tracking hard? Because it involves a lot of history of previous ones. And if you're looking for walking around for a few minutes and coming back to the same spot and seeing how much you're off in the uncompressed and the ground truth and the compressed, then that becomes the hardest to do. And we use that as a benchmark for several other things. It involves history of previous states and computes. Image detection, even that is pretty sensitive because you need to select the sharpest frame. If you have a computer vision algorithm which says, take your take your video stream and pick the sharpest one which doesn't have a blur and send it, that's actually pretty hard because if you try to compress that, small, especially when you send it, the user may zoom in and select a certain region and do. For that, it becomes pretty hard because the compression may not match the motion blur or accuracy there. It will still work, but some of your metrics on how to pick the sharpest frame that may not work. A more tolerant example, which we spoke about, is plane detection. Datasets could have periods of degradation, but the moment you slow down, the algorithm recovers because of the nature of the algorithm. As long as you get some sharp images and the motion tracking is working fine, you can detect a plane and you can put the like augmented reality object, and you could come back and the plane would still be there. So this is I hope you got the flair for how different computer vision algorithms do for compressed and uncompressed data. As I was saying in the beginning, my slide deck is uh, like this. Oh, sorry, there's one more thing which over here, which shows the device certification use case. We also use datasets for various things. When you have OEMs, such as Samsung or LG or like various phone manufacturers, right? When they want to certify their phones, then how do they do it? They do predetermined tests and make sure that the camera behaves fine. So that's another place where we do dataset compression, and we trust the dataset compression to be good enough so that it does not degrade with SNR or things like that. As an example here, what would be a good phone for augmented reality? The signal to noise ratio should be good. The histogram score should be good for various scenes. And when you move the device, the tracking metrics should not go down. These are the various things which they do with dataset compression. So that actually concludes my talk. We covered the various datasets for computer vision, the purposes, uncompressed versus compressed, the advantages of each, optimal trade-offs with motion tracking and plane detection in mind. And before I go to the open discussion, let me put back to the step for the AR core resources so that I'm open to doing. Thank you for listening patiently to my thing. I'm open to answer any questions as needed. I'm not going to be taking the full 1 hour.